something really fascinating in machine learning, foundation models.
Right.
These huge networks, trained on just colossal data sets, they can adapt to this incredible range of tasks.
Yeah, it's pretty staggering. Language, images.
Exactly. And often with just a little extra training, or sometimes, and this is the really wild part, just by seeing examples within the input itself.
That in-context learning bit, it really does feel almost magical, especially with the big language models.
It does. The way these transformer models learn and adjust basically on the fly, just from the context around them. It's pretty profound.
Yeah, it suggests they're not just, passively crunching data. They seem to be actively figuring out new patterns right there in the sequence.
Which brings us neatly to the big question for today's dive. How? How do they actually do that? What's the mechanism behind this in-context learning capability?
Well, our sources today point towards a really compelling and I think quite innovative idea called mesa-optimization.
Mesa-optimization. Okay, let's try and unpack that.
So the core idea, right, is that during their main massive training phase, what we call base optimization, these transformers aren't just learning to, say, predict the next word.
Okay.
They're also sort of implicitly developing an internal optimization algorithm.
Like a hidden learning process inside the main one.
Exactly. Think of it like a tiny learning machine tucked away inside the bigger system. And that internal algorithm is what they're calling the Mesa optimizer.
Got it. So this Mesa optimizer, it's learned, not programmed in.
Precisely. And it allows the transformer to do really rapid sequence-specific learning directly from the context it's given.
So when you feed a large language model a few examples, like translate this sentence like this.
Yeah, according to this theory, it's not just soaking that up passively, it's actually using its internal Mesa optimizer to figure out the underlying rule from those examples and then apply it.
Wow. Okay, that suggests a pretty fundamental shift, right? They're actively problem solving within the context.
It really does. It's less about just recalling patterns and more about actively computing solutions on the fly.
So our mission today is basically to dig into the evidence for this. Where's the proof, or at least the strong hints, of Mesa optimization inside transformers?
Exactly. We'll look at how researchers are using math, empirical tests, different model types, different tasks, all trying to shed light on this hidden learning mechanism. It's definitely cutting edge stuff.
All right, let's dive in. Where do we start with the hypothesis itself?
Okay, so the core hypothesis, as the sources lay it out, trained transformers seem to learn this sequence of internal parameters. Let's call them phi.
C, okay, internal parameters.
And they learn these by trying to minimize an objective function within the context LT using gradient information. So using the direction of improvement for that specific context, represented as L field.
Okay, wait, so these phi parameters, what's really innovative, you're saying, is that this whole in-context learning thing isn't something the designers explicitly built in.
Not at all. That's the kicker. It's not like there's a module labeled learn from context. It seems to just emerge, a byproduct of that huge initial training, the base optimization.
Huh, okay. And these phi parameters, what are they like?
You can think of them as a kind of fast temporary memory or weight specific to the sequence being processed right now.
Ah, so not like the main transformer weights, which are fixed after training.
Exactly. These phi parameters are dynamic. They live in the model's short-term memory, adapting to the current input. And that's what allows for that super fast adaptation we see with in-context learning.
Interesting. Now, the sources also bring up something called the token binding mechanism. Sounds important. How does that fit in?
Yeah, this is another really insightful, innovative piece. It seems the initial layers of these trained transformers develop this ability to bind input tokens to specific internal representations.
Binding tokens, like associating them.
Kind of, yeah. It's about setting up the right internal state based on the input tokens, preparing the ground for the later in-context learning. And what's fascinating is that research connects this directly to the first layer of something called the induction head circuits.
Induction heads, right? Those are known to be important for copying information from the context.
Exactly. And this whole token binding idea linked to induction heads has actually spurred development of completely new neural network designs. It's quite influential.
And it's not just a coincidence that this binding appears, right? The sources say its emergence is significant.
Very significant. The research clearly shows that when this token binding mechanism starts to form during training, the model's ability to perform in-context learning gets noticeably better. They seem strongly linked.
Okay, so let's connect the dots. We have the Mesa optimization idea, this internal optimizer. How does token binding relate?
Well, the theory interprets token binding as the transformer basically building its own little training set on the fly from the context. It's setting up the input-output examples internally.
Ah, so it identifies the relevant pairs first.
Right, it constructs this internal data set. And once that's done, the mesa objective function, that LT, is defined based on those pairs. Then, the internal mesa optimizer can kick in and work on minimizing that objective to make predictions.
Okay, so you've got a hypothesis, this token binding prep stage. What about the actual evidence? The sources mentioned looking at simplified linear attention only models. Why there?
That's a key innovation in the methodology. These linear models are, well, simpler. They're easier to analyze mathematically than the standard complex softmax attention models.
Makes sense. Easier to peek under the hood.
Exactly. So they focused on models where attention is linear. And importantly, they used a specific input format, an aggregate token input, that combines the current token with some immediate past context.
Why that specific format?
Because it lines up nicely with the assumptions of their mathematical theory of mesa optimization. It lets them test the core ideas more directly.
Okay. And how did they actually look for this internal optimization? Like, what was the test?
They used a technique called linear probing. Basically, you train a very simple linear model to predict something specific from the transformer's internal hidden states at different layers.
Like putting little sensors inside the network?
Kind of, yeah. The idea is if the transformer is doing some kind of internal optimization step by step through its layers, you should be able to see signs of that process in its activations.
And they used two types of these probes, these sensors.
That's right, two main types. The first one was trying to measure optimization progress.
How?
They tried to predict the next token directly from the representations at each layer. The thinking was if optimization is happening layer by layer, the predictions should get better, more accurate as you go deeper into the network.
Okay, that makes sense. Closer to the final output. And the second type of probe.
Those were called preconditioning probes, a bit more technical. They tried to predict a mathematically preconditioned version of the input token.
Preconditioned, what's that about?
Preconditioning is a technique used in optimization algorithms to basically make the problem easier to solve, to find the minimum faster. It adjusts the search direction based on the shape of the error landscape. So this probe was checking if the transformer was doing something smarter than just basic gradient descent internally.
Got it. Looking for signs of a more advanced optimization strategy. So what did they find with these probes in the linear models?
The results were pretty striking, actually. Strong support for the hypothesis. Both types of probes work,
Meaning?
meaning the linear models trained on the internal states could predict the target values. And crucially, the accuracy of these predictions improved both as the input sequence got longer and as they probed deeper layers in the network.
Ah, so progress across layers and with more context. That really does sound like iterative optimization happening inside.
Exactly. It strongly suggests something like that is going on.
So what was the big takeaway from these linear models about the kind of optimization algorithm the transformer learned?
Their conclusion, and this is another key innovative insight, was that the base optimization process seems to discover a kind of hybrid algorithm.
Hybrid?
Yeah. It seems to do two things at once. Across the layers, it descends the mesa objective LT, trying to minimize the error for that context. But at the same time, it also seems to improve the condition number of that internal optimization problem.
Improving the condition number. That makes the optimization faster and more stable, right?
Precisely. It makes the problem better behaved, easier to solve quickly. So it's not just naively applying gradient steps, it's learned an efficient way to optimize internally.
That's really fascinating. Okay, but these are simplified linear models. How does this connect back to the standard softmax transformers we use every day?
Good question. That's the crucial bridge they needed to build. So they compared the performance, specifically next token prediction error, of standard softmax transformers against these softmax mesa hybrid transformers.
Hybrid meaning?
Typically, these hybrids would have a standard softmax attention layer first, maybe for that token binding we discussed, and then subsequent layers would be either linear attention or these explicit mesa layers based on their theory.
And they tested these across different kinds of problems.
Yes, three main types. Straightforward linear systems where you only see part of the state, and even nonlinear systems, covering a range of complexities.
And what did that comparison show? Does the Mesa idea hold up in more standard architectures?
The really interesting finding was that this hybrid mesa architecture performed really well. It was consistently a strong baseline across all three task types.
Strong baseline meaning competitive with the pure softmax models.
Yes, competitive with, and in some cases even better than, the pure softmax transformers. This is pretty significant. It suggests the core ideas of mesa optimization seen in the simpler linear models might actually be relevant and beneficial even within the more complex softmax world.
So the advantages aren't just theoretical or limited to simple cases.
It seems not. It adds weight to the idea that this internal optimization could be a general principle at play.
Okay, this idea of internal optimization, it reminds me of something else I've heard about, declarative nodes in machine learning. Is there a connection?
There absolutely is, and it's another innovative angle that researchers explore. A declarative node is basically a layer in a neural network whose output isn't calculated directly by some fixed formula.
Okay.
Instead, its output is implicitly defined as the solution to an optimization problem. So you're kind of embedding an optimizer right into the network structure.
Ah, I see. Instead of just matrix multiplications and nonlinearities, one layer is an optimization solver.
Exactly. And the researchers propose that their mesa layer, the one implementing this learned internal optimization, is essentially an example of a declarative node, specifically within attention models.
And what are the potential benefits of thinking about it that way?
Well, potentially efficiency. You might replace a whole stack of standard layers with a single mesa layer that just computes the optimized result directly. And maybe interpretability too, because the layer's function is defined by a clear optimization goal, not just a complex series of learned weights.
That's a really neat framing. Now, the sources naturally get into the math behind this. We don't need to drown in equations, but can you give us a feel for the key mathematical ideas, especially the novel parts?
Sure, they formalize how those internal parameters, phi, get updated to minimize the in-context objective, LT. A key innovation is how they derive expressions to compute this update causally, meaning only using past information.
Causally, right. Important for sequence processing.
Very. And this involves introducing what they call forget factors, represented by gamma. These basically control how much influence past inputs have on the current internal optimization step.
So these forget factors are part of the causal masking, but maybe a more nuanced version.
Exactly. Standard causal masking just cuts off the future entirely. These forget factors allow for a more sophisticated weighting of the past within the mesa optimization process itself. They also work out how to calculate gradients with respect to everything queries, keys, even these forget factors, showing it involves some complex recursive calculations.
And they connect it back to standard gradient descent.
Yes, they actually derive a mathematical relationship showing how the mesa optimizer's updates relate to gradient descent steps on the mesa objective, which helps ground the theory.
Okay, that paints a clear picture of the mathematical underpinnings. Now, there was also a surprising twist, wasn't there? Something about fixed teacher linear dynamics.
Ah, yes. That was quite unexpected. They looked at transformers trained specifically on data generated by a single fixed linear system. Like the underlying rules never change.
Okay, a very stable, predictable environment.
Right. And in those models, they found surprisingly little evidence for mesa optimization.
Really. Even though the model learned to predict the system's behavior.
Apparently so. Its performance wasn't particularly explained well by the mesa optimization framework, unlike in other settings. Simple gradient descent steps seemed to match its behavior better, and the internal weight structures didn't show the same patterns.
Huh. So the model learned the task, but maybe not by learning an internal optimizer in that specific case.
That seems to be the implication. And it's really interesting because it suggests the dynamics of the training data itself might be crucial. Meaning maybe you need a certain amount of change or variation or complexity in the training data for the transformer to find it beneficial to learn this meta-level skill of internal optimization. If the task is too simple or static, maybe it just learns the direct mapping.
That highlights how important the training environment is in shaping how these models learn.
Absolutely. It's not just about the architecture, but what you feed it.
The research also mentioned an innovative technique called linearizing softmax transformers. What was that about?
Yeah, this was pretty neat. They took pre-trained standard softmax attention layers and then trained linear attention layers to mimic their behavior. It's a process called distillation.
Trying to capture the essence of the softmax layer in a simpler linear form.
Exactly. And what they found was that these distilled linear layers ended up having structural similarities to the original softmax layers, suggesting there might be some underlying connection, maybe related to these optimization principles, between how both linear and softmax attention work, even though they seem quite different on the surface. It hints at potentially deeper shared mechanisms.
Okay, and wrapping up the empirical side, they also looked at more complex scenarios, right? Partially observable systems, nonlinear ones, and even actual language modeling.
Yes, they pushed the analysis into more realistic territory. For the partially observable and nonlinear systems, they again found that those hybrid softmax mesa architectures performed well. It showed the theory wasn't just for clean, fully observed linear cases.
And for language modeling, like on a big data set like the pile.
Yeah, they did experiments there too. They built hybrid models, typically softmax attention in the first layer, then linear or mesa layers after that.
Why softmax in the first layer specifically?
Consistent with that idea that the first layer might be crucial for the token binding or setting up the problem for the internal optimizer.
Right. And how did these hybrid language models do?
They found that these hybrids, with roughly the same number of parameters as pure softmax models, were actually competitive in terms of performance.
So you don't necessarily lose out by incorporating these MESA principles.
It seems not, at least in their experiments. They also noted seeing interesting copying patterns in the attention maps of that first softmax layer, which again fits the story of it identifying key input-output pairs for in-context learning.
Okay, so let's try and pull this all together. Summarizing this deep dive, the main takeaway seems to be this growing, compelling evidence that transformers might be learning these implicit optimization algorithms, mesa optimizers during training.
Right, and that this learned internal process is what enables that amazing in-context learning we see.
And the evidence comes from the theoretical work, the success in the simplified linear models using those probes.
And importantly, the strong performance of those hybrid softmax mesa models across different tasks, even complex ones like language modeling. It holds together pretty well.
Yeah, though it's also crucial to remember that surprising result with the fixed teacher linear dynamics.
Definitely, that really underscores how the nature of the training data might be key to whether these mesa optimizers actually emerge. It's not guaranteed.
And that idea of the mesa layer as a declarative node, that feels like a genuinely innovative way to think about network layers, potentially opening doors for efficiency and maybe even better interpretability down the line.
Absolutely. It reframes a part of the network not just as computation, but as embedded optimization. It really does open up a lot of fascinating questions and directions for future AI research.
Which leads us nicely to our final thought for you, the listener. Thinking about all this, what are the bigger implications here for how we understand intelligence, even artificial intelligence?
Yeah, if models are learning to learn internally, what does that really mean?
Could we eventually design AI systems to explicitly leverage these kinds of internal optimization processes? Could that lead to even more adaptable, more efficient learning?
It's definitely food for thought. Makes you want to dig into the original papers and see where this research heads next.
Absolutely. Plenty to chew on there. Thanks for joining us on the deep dive.